Now let us move to the second topic, that is pressure and head. In this topic, we are only looking at the hydrostatic fluids. That means we are only looking at fluids at rest. If the fluid is at rest, we know the sum of forces acting on it is 0. However, from the definition of fluids, if it is not moving, then there are no shear forces. Therefore, the forces exerted at boundaries are perpendicular to the boundary. So the pressure forces are perpendicular to the surface. What is pressure? Pressure, usually denoted by P, is equal to the force exerted divided by the area of boundary perpendicular to the force. Therefore, the units of pressure is newtons per square meters or pascals. However, there are two other units to express pressure. They are ATM, that is atmosphere, or bars. Now the conversion for these units are 1 ATM is equal to 1 bar is equal to 10 to the power 5 of pascals. Now let us look at the Pascal's law. What is Pascal's law? It says pressure is isotropic. That means pressure does not depend on orientation. Now in fluid mechanics, we are not buying any theories or any laws. We want to prove it. So let's try to prove this Pascal's law. As shown in this figure, consider a fluid wedge from a fluid at rest. So that means it is not moving. Since it is in equilibrium, the summation of forces in a particular direction should be equal to 0. Let us calculate the forces acting on each surface. If we consider this Fx, it is going to be equal to the pressure Px into the area, that is delta y into delta z. Similarly, Fy is equal to Py, pressure acting on this plane, into delta x and delta z. Fs is equal to Ps delta s delta z. If we consider the equilibrium in horizontal direction, we'll find out that Ps is equal to Px. Now we haven't defined this theta, therefore it can be for any theta. That means the pressure is isotropic. Now let us look at the pressure variation with depth. Consider a stack of fluid particles forming a column of height h reaching up to the surface. Now force on the shaded area due to its self-weight is rho gh delta x delta z. That is from the density. Rho is equal to m over volume. So if we need to calculate m, we know it is rho into volume. If we need to calculate the weight, that is rho volume into gravity. Now, that is the downward force. Let us find the upward force acting on this plane. It is the pressure force. Suppose the pressure is P acting on delta Z, delta X area. So the pressure force is P delta X delta Z. Now if it is not moving, we can equate these two forces. That gives us P is equal to rho GH. Now if we consider the density of a fluid is constant, which is incompressible, P is equal to rho GH has a variation of y is equal to mx. We call this pressure to be the gauge pressure. But when we consider the pressure at the surface, the variation becomes P is equal to PATM plus rho GH. PATM is the pressure at the surface, or it is the atmospheric pressure. Now the function is y is equal to mx plus c. We call this y to be the absolute pressure. Therefore, the absolute pressure is equal to gauge pressure plus atmospheric pressure. Now let us look at the pressure variation across two liquids. The variation has two gradients. And please understand the gradients with respect to the densities. We know higher density liquid is at the bottom. Therefore, the gradient of that liquid has to be higher than the top liquid. But please understand the variation. Now, usual y direction is the x for this one, and usual minus x direction is the y for this variation.